In this recording, we're going to look at the fact that group homomorphisms send inverses to inverses. In other words, we're going to prove the theorem that says the following. If G and H are groups, and F going from G to H is a group homomorphism, then F of G inverse is going to be equal to F of G's inverse for all G inside the domain group G. It's important to understand that this particular inverse is in group G, but this particular inverse is in group H. So the thing that we want to do here is we want to start off with remembering one thing from the last video. So from the last video, we saw that if F takes G into H is a group homomorphism, then F of the group identity in G is the group identity in H. And we're going to need that particular result to prove our main theorem. So the proof of our main theorem, we're going to let G be any arbitrary element of capital G. And so what we know is that we know that G times G inverse is equal to the identity inside capital G. And so what that says is that F of G times G inverse is equal to F of E sub capital G. But in that last video, we wound up showing that this particular thing is known to be E sub capital H. So at this point, we know that F of G inverse is equal to E sub H. But F is a group homomorphism, so we also know that this expression here can be rewritten as F of G times F of G inverse, and that's got to be equal to E sub H. Now, the fact that F takes elements in G into elements in H means there exists an H inside capital H such that F of G is equal to little h. And using that, we can rewrite this equation as H times F of G inverse is going to be equal to EH. Well, what we're now going to do is we're now going to pre-multiply by H inverse, which has to exist because H is a group. So we get this equation. H inverse times F of G inverse is equal to H inverse times EH. Of course, this is going to imply that E sub H times F of G inverse is equal to H inverse. And of course, EH times anything in H is just the other anything. So we now have F of G inverse is equal to H inverse. But remember that up here, we've written that F of G is equal to H. And so substituting that back in, we have that this side here becomes F of G inverse. And so what we now wind up having is we are indeed have shown that F of G inverse is equal to F of G's inverse. And that completes this particular proof.